So welcome. I'm Fred Moyer. I'm a developer evangelist at Circonus, which means I'm an engineer who talks to people. Today I'm going to be talking about how to do latency SLOs the right way. I want to give a shout out to my colleague Heinrich Hartmann, who's a data scientist and originally came up with some of this material for a blog post. So latency. Who here thinks that measuring latency for their applications is an important metric? A lot of folks? I would expect so. So for any of your services, let me ask you this. Can you say over the past 24 hours or the past week, how many requests were served within about 550 milliseconds over the last month? That's kind of a specific question, but I'm guessing that folks here have an idea of certain thresholds that their service needs to comply with to get good service. But let me ask you, can you answer this question if I said, here's a threshold, I want to know how well your service is going to perform. Do you have the tools to do that? Probably most folks here do. I mean, this is an observability workshop. And with those tools, can you ask yourself, how accurate is your answer going to be? How accurate does your answer need to be for your application? Because we're all working in different industries. We're not all Google. We don't process trillions of requests per day. So accuracy is relative to your business application. So today I'm going to talk about how to calculate SLOs the right way. I'm going to do a quick SLO refresher. I'm going to go over a common mistake people run into when trying to do this. And I'm going to talk about computing SLOs with 3 different methods. So let's get started. So Google SRE book came out quite a while ago. It was kind of a seminal work on SRE, and it defined 3 essential terms in there. SLI, service level indicator, SLO, service level objective, and SLA, service level agreement. And I'm going to talk a little bit about each of these. There's 2 other important books on this subject that go into SLOs a fair amount. Seeking SRE has a chapter by Theo Schlossnagel, the guy who brought me into this stuff a few years ago. Goes into how you can generate deeply technical service level objectives. The Site Reliability Workbook has a whole chapter on SLOs. So if you're not that familiar with SLOs, you should go and read these books. They've got some great work there. So a while ago, Liz Fong-Jones and Seth Fargo produced this YouTube video, SLOs, SLAs, oh my, which really talks about how these 3 things are related. And the core concept that they used was SLIs drive SLOs, which inform SLAs. So what's an SLI? It's a service level indicator. It's how I can express my service in terms of a metric, particularly a latency metric. An example is my 95th percentile or 99th percentile homepage requests over the past 5 minutes should be less than 300 milliseconds. And a service level objective is a target that I want to hit for that. I want to reach my SLI 99.9% over the past year, which means that I can take the past year, divide it up into 1,000 pieces, and I need to hit that SLI for 999 of those. And SLAs are just an extension of SLOs. That's a legal contract and essentially it's a relaxed SLO, because technically or typically lawyers will get involved and they'll say, well, that's nice that you want to try to get this number, but let's take 50% off of this so we don't have to pay out credits to people who are using our service. So that's kind of a quick jump through SLOs. How many folks here have documented SLOs that they're using with their services? Good, more than I would expect. So let's take a look at a common mistake that I see people running into when getting into this in this area. And that is averaging percentiles. I see this popping up a lot on Reddit, on Hacker News. People will say, well, in this one particular case, you can average your percentiles and get a meaningful answer. But you cannot do this. don't go out there and do this. You know, I've got a nice math equation up there that says, hey, my P95 of, you know, set W1 union with set W2 is not equal to P95 W1 plus W2 over 2. That equation works maybe, you know, a few % of the time. If you've got homogeneous workloads across your nodes, or you've got a service that's very consistent, you can go ahead and do that. But the problem is, if your workloads become asymmetric, or you've got you know, a variance in those workloads over time, this equation is going to fail, and it's going to lie to you. So I'll tell you up front, you know, be very cautious of this. I know folks here are probably more experienced practitioners, but you know, I still see this happen quite a bit. So here I've got a graph. I've got P99 of request latency, P95, P90, and a median. And this is, you know, over about 24 hours. So you'll notice that the P99, you know, that hangs out around 180 microseconds and then goes up to around 300 microseconds for maybe a few hours. Now, if I said, hey, what do you think the P99 is over this 24-hour time span? You might be tempted to say, like, well, you know, it's probably, you know, it does jump up a little bit, so I can probably take a guess and say that, you know, it's around 200 microseconds. It seems reasonable. You know, I'm taking an average. But then what if I came back and I told you that 90% of the requests occurred when that P99 jumped up to 300 microseconds? Well, it kind of makes sense. You know, I've got a whole bunch of requests coming in, and my P99 goes up. That's how systems, you know, often behave. So, you know, this is a good example of how, you know, complexity can be masked behind a simple percentiles graph. Same thing for, you know, percentiles across different nodes. You know, here I've got, you know, a histogram distribution of, you know, request times for, you know, say, blue web server and red web server. You know, P95 is a lot higher for red web server. So what about these things? You know, do I get, you know, can I average these? What happens if I try to do that? Well, let's say, you know, my blue P95 is around 220 milliseconds, red P95 is 650. My average there is 430, but if I take all these samples and aggregate them, I get 230. That's almost, you know, double. That's a huge error, especially when you're trying to deal with something like SLOs, which get derived down to SLAs, which have legal implications. You know, so this is, you know, this is a common mistake that people make, and you know, you might ask yourself, well, you know, I'm experienced. I'm not going to make this mistake. How do, you know? But how do people fall into this? Well, one way is, you know, a lot of the tools at their disposal make this very easy to do. Say if I've got a log parser that I hook MTail to, which is a Google open source tool that I can essentially extract latency data from that log file. You know, that'll give me, hey, here's your P99, here's your average. You know, it gives me, you know, dozens or, you know, hundreds of different metrics that I can store. Well, which one of those do I store? You know, I have to choose from one of these available ones. And, you know, if you're inexperienced, you might just decide to, like, take some open source code, glue it together, and start storing metrics, which I've never seen that done in the past. Actually, I have a lot. So, you know, this is kind of the trap that the tools out there we provide cause people to fall into it. So we took a look at a common mistake. Let's see how to do things the right way. First, by computing SLOs with log data. So, you know, this is an example Apache log format. You know, we track our request latency in milliseconds right there. You know, this one log line is about 100 bytes. You know, it hasn't been optimized with nanolog. Shout out to that. But you know, if we have about 100 or 10 million requests here, you know, it's about a gig. Not, you know, a huge amount, but it's got some mass to it. And for an API, this could be, you know, still be considered small. But what if you're serving a web page here, and each web page makes, you know, 50 sub requests? Now all of a sudden I've got 50 gigs I'm dealing with. So that's a, you know, that's a fair mass of data. And the way most people handle this is they'll take the logs, they'll shove them in HDFS or shove them in Logstash or Splunk, and then they'll aggregate them in a central log server. And I can go through there, and if I've got an SLI of 550 milliseconds, I can run this grep and awk command and say like, hey, tell me how many of my requests exceeded that. Fairly simple thing to do, and it'll give you the right answer. But one of the downsides of this approach is it's very heavy. You need a lot of servers. And anyone who's dealt with commercial log parsers out there, say Splunk, know you can quite quickly generate a fairly large bill. But this approach is good, and that it makes it very easy to calculate my SLI. All I have to do is specify a time window, say 24 hours, sort all my samples by value, and then find the sample that is 5% by count from the highest sample. That's my P95. That's a very straightforward calculation to do. And I can take that SLI and I can apply it over different time windows, and I can see for which ones of those time windows it succeeds, and I can determine pretty easily like if I've met my SLO. This is some very straightforward math, very easy to implement. And so this is actually, well, it's a bit computationally intensive approach, and not that economically efficient. It's one that produces a correct result. So the pros of this, it's very easy to configure logs to capture latency. Anyone here can do that easily. It's easy to roll your own processing code. Some tools out there like Splunk or Elasticsearch, already have built-in P95 or quantile functions, and it gives you accurate results. So this is a good approach. The cons of it are it's expensive. You can use sampling to reduce the amount of data that you're processing, but I wouldn't recommend it because if you're sampling, say like on a per second basis, like I'm going to grab 10 samples every second, you're going to miss a lot of data when the load gets really heavy, is kind of how I demonstrated. This approach is not fast, and this approach is difficult to scale. So let's take a look at another approach, which is computing SLOs by counting requests. So this is another computationally pretty cognitively easy approach to understand. We have two counters, one that counts the number of requests that violated my SLI threshold. Say if I set my threshold at 30 milliseconds, I just keep a running count of how many requests violated that. And then I count the total number of requests. And then I divide those to multiply it times 100 and subtract it from 100. And this approach is kind of conceptually similar to the Prometheus cumulative LE style histograms, where you specify, I think typically maybe half a dozen thresholds, and you count the number of requests that fall below each threshold. It's pretty simple. Here's a visualization of it, which you've probably seen done with any number of monitoring tools out there. I've got my number of requests that violated my SLI in red. I've got my total number of requests there. Easy to graph. And I can take that and I can say, hey, I had 96.2% of my requests that met my SLI, and therefore I met my SLO. So this is conceptually a very easy way to accurately calculate your SLO. And so let's take a look at the pros and cons. It's simple to implement. Very basic arithmetic. It's performant. You've got two counters. It's really easy to increment those per request. You do have to instrument your code, but a lot of application frameworks do have, something that can count the total number of requests. So really, you just have to add the one that counts the number that violated your SLO. It's scalable. I've got two counters. I can each have a 64-bit int. That's very low memory usage-wise, and it's accurate. This is going to get me a result that is extremely accurate every single time. It's got some cons, though, and mainly that you are working with a fixed SLO threshold. So if I want to go ahead and change that, I have to go back in and either reconfigure my code or re-instrument, and it also makes historical look back impossible. But given that, this is also something that you can implement with most commercial and open source monitoring tools out there. I know that because I've done that. So this is, I think in contrast to logs, this is computationally efficient, but quite a bit more inflexible. So let's move on, and let's talk about computing SLOs with histograms. I've seen several talks here today that talked about histograms, and since we are in Washington, I kind of want to go Steve Ballmer and say histograms, histograms, histograms. But seriously though, I was very happy to see that histograms are getting talked about more. This is a histogram. Everyone's seen one of these? It's kind of a simplified version. It's essentially a bar chart. I've got the number of samples on the y-axis, and then I've got my latency value on the x-axis. I've got my mean, which is the average value, the median, the 50th percentile. The cube 0.5 is just quantile notation. I've got my 90th percentile represented as cube 0.9. That just means 90% of the samples are below there. And I've got my maximum Q1. The sample counts are in each of these, the bars are called bins or buckets. Wikipedia says bins. Other people say buckets. It doesn't really matter. Guillotine has an excellent site, hdrhistogram.org, which details his open source Java logged linear histogram. He's also got an excellent video on how to use histograms to monitor latency. There's several different types of histograms. Linear, approximate, fixed bin, cumulative, log linear. These aren't necessarily fixed types. These are more attributes that you can use to define and describe histograms. For example, the Prometheus style histogram, it's cumulative and fixed bin. Approximate histograms, the most popular one out there, I think, is probably Ted Dunning's T-Digest. And then there's log linear histograms and linear histograms, which I think we saw a couple examples of linear histograms in earlier presentations. This is a log linear histogram that we've implemented at Circonus. Can everyone see the delineations between the bins? So essentially, what I have here is latency data for a set of load balancers over a period of time, graphed here. And I've got bins between that are increasing exponentially by a factor of 10 every power of 10. So between 100,000 and 1 million, I have 90 bins, each with a width of 10,000. And originally when I looked at this, I said 90, why not 100? Because it's 1 million minus 100,000, which is 900,000, and it's a little bit neater for the math to divide it into 90 spots instead of 100. And then so you'll notice at the 1 million boundary on the x-axis, the bin size increases by a factor of 10. And so what this allows us to do is have a very wide range of values that we can represent, but still be statistically significant. And the implementations for this are on GitHub below. The C version is on the top, Golang version is on the bottom. And I've overlaid some common aggregates there. The average is at 500,000. The median's around 600,000. This is a non-normal distribution, a Poisson type distribution, if I recall correctly. And then we've got our 90th percentile out there at 1 million. And this is a very space efficient data structure. I've got about 50 million data samples in here, 50 million time series data samples. And the nice thing about the histogram is it's largely space invariant for the number of samples. The amount of space that it occupies in memory is more dependent on the span of how many bins you have. Typically for operational time series data like this, we see spans around 300 bins or so. And so I can capture, I don't know, 50 million data samples here, statistically significant, and I don't know, like a few dozen megs. So it's a very space efficient structure. Histograms also have a property called mergeability, which means I can take data from yesterday in a histogram, I can take data from today, and as long as they have this exact same bin boundaries, I can merge them together, which just means that I go through each bin and add up the count for each corresponding bin. And I can not only do that for aggregating them across time, but I can do that across space. So I can take, if I've got 10 load balancers, I can take histogram data from each of them and just add up the bins and combine them, and then get the calculate my 90th percentile across the entire cluster. So this is a very strong property of histograms. But how do we calculate SLOs from those? And you might think, well, this is complicated stuff. The math is going to be kind of rough, but it's actually not. If I want to say how many requests, in here are faster than 330 milliseconds, I've got microseconds on the x-axis. It's simple to calculate this. I walk the bins from lowest value to highest until I reach, my SLI on the x-axis, and then I take all of those counts in each bin, and I sum them up, and I'm done. I've got how many requests? That was easy. Of course, there's a little devil's in the details. I gave this lightning version of this talk a few months ago at New Ops Days, and Liz Jones said, hey, this is good stuff, but you also have to remember that you need to make sure that your SLI is on a bin boundary because you're counting up all these bins. And you need to know what your binning algorithm is. And that's a good point. But I can calculate in between bins by just interpolating across bin boundaries. It's simple junior high or high school algebra. I just take the count on one side, the count on the other side, and the values, and I calculate a linear line between those, and that gives me that extra value that I tack onto the end. And if we have a little bit of extra time, I can show the code. So what are the bin boundaries of a long linear histogram like this? So for the implementation I've shown, we have bins at 320, 330, 340. So luckily I landed on one of the bin boundaries. But because it's log linear, it's every factor of 10. We have 90 bins. So I've also got them at 10, 11, 12, and 13. And I've also got them at 10 millions, if I'm showing that right, 11 millions, 12 millions. So this allows me to get a very precise statistical representation across a very wide range of values. In our implementation, we have this implemented to plus or minus 128. So it's pretty wide. And one of the other interesting things about this is, this makes. Sorry, I should have my notes on that one. I'll get back to that. So let's take a look at what are the advantages of computing SLOs with histograms? They're very space efficient. Each histogram is about 300 bytes. About 10 times more efficient than logs. We've got a lot of flexibility. We don't have to specify our thresholds up front. And we can apply a lot of statistical methods. I can calculate my P90 from that. I can do an inverse quantile. I can do an interquartile range, which is basically saying, where's my 25th, 50th, 75th percentiles? I can calculate standard deviations. I can apply a number of statistical methods to this. They're mergeable, which means I can aggregate data across nodes. And this structure is very performant. The C implementation developed, it takes about a nanosecond to do an insertion. Quantiles can be calculated in microseconds because it's a fairly simple operation. Oh, that's what I was going to talk about, errors. The errors are generally bounded at a maximum of about 5%. I'll take the bins at 10 and 11 as an example. If I've only got data, that comes in at 10.99, I'm going to insert that into the bin bounded by 10 and 11. And that's interpolated to that averages out for the bin to be about 10.5. So what's 10.5, minus 10 over 100? That's about 5%. That's the worst case error. And that's not something you're really going to see in practice. Generally, the wider range of data you have, the number of bins, the lower your error is going to be. And there's also several open source libraries available for these. I've got the log linear one I mentioned. There's Guillotine's, HDR histogram, Java implementation. There's Ted Dunning's tdigest approximate histogram. That's also open source. So there's quite a few advantages to this approach. There are some disadvantages. The math is a little bit more complex than the other methods, though not really so much for stuff like tdigest is definitely more complicated, and you have a little bit of loss of accuracy. So let's take a look at how we can do some of these calculations with Python. We've published Python bindings to our C library, which you can install with pip. You do have to have the C library installed beforehand. I'm not sure if anyone solved the C dependency for Python modules, how to install those automatically. But I can write some Python code that looks like this. I can make a new histogram structure. I can insert some values into it. And then I can call simple methods like count, sum, and I can calculate my median just by calling this quantile method. So this is an open source implementation that is pretty easy to get going with. And I can take it a little bit more complicated. I can pull in PyPlot. It's not GNU-plot, but that works too. And I can, if I've got, say 10,000 latency data points, I can go ahead and insert each of those into the histogram structure, and I can go ahead and call this plot method on it. And I can also, calculate my 95th percentile and overlay that. And I'll show you what that looks like. That's the same plot I showed earlier in the presentation. This was actually generated using that code. So it's pretty flexible, easy to get out there and take a look at the data that you do have. So some conclusions. Averaging percentiles, tempting, but misleading. Don't do it. Counters can be used to calculate SLOs correctly. It's a really easy approach, but it's a little bit inflexible. Histograms give you the most flexibility in terms of choosing latency thresholds, but there's only a few libraries out there that you can use to implement them. Support for what I call sparsely encoded histograms, which is where you're only recording data where the bins actually have data, or something like high density histograms. The support isn't really out there in time series databases. IronDB does have log linear histogram support. But it is pretty easy to serialize histogram data and store it in any sort of other data store. So that's about it. I got a few minutes for questions. I do have some other, if you want to learn more about histograms, I have some more detailed presentations up on my SlideShare account.
Questions, there's a question. Are they here? Oh, they are. Oh, good. The Expedia folks are here. Hooray. All right, questions. Who had a question?
Thanks for the presentation. Sure. I just have a quick question. Are you applying the error budget on top of the calculation for SLI and SLO?
I'm not applying the error budget in any of the calculations that I showed.
Okay, thanks.
Is there a charger? Yes, we'll get you one. Yeah.
Question was, am I applying the error budget on top of any of the calculations I showed?
Yeah. The question was if they apply it on top of
Okay. Oh, do you need me to repeat the question?
So yeah, the question was, do you apply the error budget on top of the calculation for the SLOs and SLIs?
No, I don't.
Sorry about that. Anybody else?
How many folks here use Prometheus? So here's a question I've gotten about this. Sorry to interrupt. You know, it's got fixed bin histogram boundaries. How should I deal with that? My answer is make a lot of them.
Quick question for INDB. When you store these histograms, do you actually store every bucket that has a value in it? Or, because I know with like QDigest or TDigest, they sometimes, when you have enough values, they'll combine buckets to sort of reduce the amount of storage required, but at the cost of some accuracy.
We only store bins that have data in them.
But you'll store every bin that has data in them. You won't combine some bins.
We do, yeah. We do not combine bins.
Okay.
We don't do approximations.
Cool.
But we only store bins that have data,
Yep.
which is why it's called sparsely encoded.
Great. Anyone else? I think we've got time for one more. No? I think we're good. All
Thanks,
right.
folks.
Everyone give it up for Fred.